Welcome back to ECE 320A. We have a lot to cover today, and you have quite a bit to get done, I think, before Sunday. That's homework number 3's due date. If you haven't started, I would suggest you start that assignment. There will be an information session on Monday morning at 9 a.m. in room 530. And we will be talking about technical electives, not AMP years, but AMP, the Accelerated Master's Program, and graduate school in general. That will be Monday morning, but I will try to record it if you can't make it to that particular time. There are calculator videos if you have an 89 or an Inspire that are on D2L that might help you check your work when you're doing inverse Laplace transforms. And that's what we will be doing today. But before we get into that, well, after we do a little bit of the preliminaries, before we get into all of the inverse Laplace transform material, I want to try to gain a little bit more insight or intuition into the Laplace transform, and in particular what this S variable, how you can interpret it. And we will illustrate some of those concepts with a low-pass filter example. But I should say that before we get too far into today, after Tuesday's lecture, after the last lecture, I added quite a bit more notes to the material. We didn't cover that in class, but you might look at those to see that they make sense because you will be responsible for those. It was essentially what we're covering now, a little bit as a review. Question? No, the extra notes are not a separate video. I didn't take the time to talk my way through those. It's just like another page or two beyond the class notes. It's at the bottom of the class notes. So if you're looking at those class notes from the last lecture, at the very bottom, you will see some discussion on this particular material, maybe just a little differently, that I'm going to quickly go through right now. And that is, what does the transform of an impulse and its derivatives, and what is the inverse transform related to those? What do those look like? For example, can you remind me from earlier lectures what the Laplace transform of an impulse is? That's 1, isn't it? That's pretty straightforward. Knowing that, now if I said, oh, I actually have a constant in my capital, let's say f of s expression, and I need to take that back into the time domain, that 1 is now a 1 in the frequency domain. That's in my f of s formulation. What does that look like? If you now have a constant and you're trying to inverse Laplace transform that constant, what does that mean in the time domain that that corresponds to? And that's known from the previous formula. It's the impulse. So now we're just learning how to go back and forth. This will just be then in the time domain, an impulse, and you can now go either direction. If somebody gives you an impulse in the time domain, you know that's a 1. If they give you a 1 or a 6 in the frequency domain, now that's a 6 weighting an impulse, which means that you now have an area of 6 underneath that impulse response, or a weighting of 6. Extending on that, this is what I simply sort of put down in the last of Tuesday's lecture. Suppose that we now have the derivative of the impulse. Did anyone look at those notes to know what that might equal? So now you have the derivative of an impulse, which is a very interesting concept to even think about. An impulse is an ideal waveform to begin with. Now you're differentiating this item that takes off and goes to infinity in an infinitesimally short amount of time. This is kind of a nasty beast, but you can show, and that's what I showed at the bottom of last time's lecture, this is now S in the frequency domain. If you Laplace transform the derivative of an impulse, that gives you an S in the frequency domain, which now means that if you had an S term sitting by itself in your expansion for, let's say, capital F of S, you would take that into the time domain, and that corresponds to the derivative of the impulse. And these are going to arise when we have improper transfer functions or transforms. Let's look at one more. Hopefully you'll never have to deal with this in the real world, but this is sort of a class, so we'll talk about it. What if we differentiated that again? Do you see the pattern that's developing? What would be the Laplace transform of a double derivative of the impulse? That's S squared. Now, if you see an S squared sitting by itself or scaled, you know to take that back into the time domain, that's going to be the impulse differentiated twice. Now, let's use that in an example. Suppose f of s is 5s squared plus 2 over s squared plus 6s plus 8. And before you start jumping in and doing an inverse Laplace transform, what's the first question you have to ask yourself? Pardon? Look at the order of the numerator and the denominator. And what are you hoping to see? You would like it to be strictly proper, which means the numerator has a degree strictly less than the denominator's degree. Is that the case here? No, this is actually a proper transfer function. And we are actually trying to find, maybe I should have stated that to begin with, I'm trying to go back in the other direction. I'm trying to now go into the time domain. I'm trying to find little f of t, which little f of t is now the inverse Laplace transform of this capital F of s. And you just told me then that the very first thing that you need to examine or ask is this transform strictly proper? And you just told me no, because it was proper. Meaning do you want me to give you the definition of strictly proper? Well, that makes sense if I do it in red with this curly brace under strictly proper. This means the degree of the denominator. Well, maybe I should have let me do it this way. The degree of the numerator is less than the degree of the denominator. That's the definition of strictly proper. And that's not what is happening with this, because here the numerator is second order and the denominator is second order. They have the same order. It's a proper transfer function or transform. It's not improper, but it's still not strictly proper. Because it is not strictly proper, now what do we do? What's our first step in this inverse Laplace transform process? What do we have to do? We have to do long division. Well, you could do synthetic division, but I'm just going to call it long division for now because long division is easier to keep track of. So this now says that we are doing long division, and that simply says that we take our denominator and divide that into the numerator. We are trying to find or continue to divide until the remainder term has an order strictly less than what we're dividing into the numerator. In this case, we're looking for a polynomial that has order 1 or less. And if we do this long division, s squared goes into 5s squared 5 times. We now have 5s squared plus 30s plus 40. We subtract that and we have minus 30s minus 38. We look at that result, which is our remainder so far, and in fact that has an order strictly less than the denominator order, so we can stop and we can now say, oh, capital F of s is now 5, and let me just keep the negative signs upstairs, minus 30s minus 38 over s squared plus 6s plus 8. And now we can concentrate or focus on this piece of the overall transform, capital F of s, and apply our partial fraction expansion techniques to f sub 1 because we already know how to take that into the time domain. That was what we just did up here. Which of these rows does that correspond to? The 5. The first row. So now we will end up in the time domain as 5 delta of t, 5 times the impulse. And that will be the first half of this process. And if you do have a calculator that has the proper frac function, you could now say, oh, I want 5s squared plus 2, whatever we started with, over s squared plus 6s plus 8, and it will actually give you that result. And f sub 1 is strictly proper. Now that we have that, let's look at inverse Laplace transforming f sub 1, which was minus 30s minus 38 over s squared plus 6s plus 8. Now what do we do? You can try to factor the denominator. And it may have what? What possible roots will this denominator end up with? It could be real and equal, real and unequal, or complex if it's a quadratic. In this case, do you see the factorization? 2 and 4. This now can be factored into s plus 2 times s plus 4, which now says that we are looking at a partial fraction expansion. Since those are real, distinct roots, now we can put a constant over each of those factors and try to find a1 and a2. And again, if you were fortunate enough to have mom or dad purchase you a calculator, that will find the a sub 1 and the a sub 2 for you. If you don't, then how do we find a1? what's one technique. And in this case, it's probably the most straightforward or most direct approach to find A1 directly. And that's to multiply both sides through by the factor underneath A1, which is S plus 2, and then evaluate the left-hand side that results at the value of S that causes that factor S plus 2 to vanish, or you're evaluating it at S equal minus 2. Meaning, we are now taking S plus 2 times minus 30S minus 38 all over S plus 2, S plus 4, and evaluating at S equal minus 2. This factor cancels that factor, and we end up with minus 30 times minus 2, minus 38 all over minus 2 plus 4. Or we now have 60 minus 38. That's almost minus 40. It would be 20 if it was 40. So we now have 2 more than that. It's actually 22 over 2, or A sub 1 is 11. And hopefully your calculator is turning that out. Is that true? Okay. A sub 2, same process, just a different factor. S plus 4 minus 30S minus 38 all over S plus 2, S plus 4, evaluated now at S equal to minus 4. The S plus 4 factors cancel. We have minus 30 times minus 4, minus 38 all over minus 4 plus 2. Now we have 120 minus almost 40. That would be 80 if it was. So it's now 82, or this is now minus 41. Now I can immediately write down little f of t. Should I do that, or should I show you what we have? We now have for capital F of S, that's now 5 plus 11 over S plus 2 plus a minus 41 over S plus 4. F of t is now, what's the first term in little f of t? You already told me. That's a delta function scaled by the 5. Then we have 11 times what? That's going to be a decaying exponential with a decay or an exponent of minus 2. We have 11 e to the minus 2 minus 41 e to the minus 4t, and that's true for t greater than or equal to 0. And that should just be automatic. Once you see capital F of S, you should be able to write down immediately little f of t. Let's talk a little bit more in general. Pardon? So if I try to explain A sub 2, let me go back to this. And now do you see that if I want A1, suppose I multiply both sides, left and right, in this blue and black formula by the factor S plus 2. Then the far right term becomes S plus 2 over S plus 4 times A2. But I'm evaluating that at S equal minus 2. So what happens to that term? Is that making sense? I'm now saying take this, and take this, multiply by s plus 2, s plus 2, and s plus 2. And if I now evaluate that, boy, this is getting kind of messy, but at s equal minus 2, s equal minus 2, s equal minus 2, do you see what falls out? This cancels that, and it isolates a sub 1. The far right-hand term, now s plus 4, that's well behaved in the denominator. That's just 2. But the numerator is 0 now because it's s plus 2 evaluated at minus 2. So the a sub 2 term goes away. That's how we're isolating a sub 1. And then the blue, red, and green on the left is exactly how we were equating the formula for a sub 1 to begin with. We said take the expression for, in this case, capital F sub 1 of s, multiply it by the factor s plus 2. That will now allow me to cancel those two factors in the numerator and denominator and evaluate what's left at the value of s that causes that to vanish. Did that help? That's how you now find these partial fraction expansion coefficients, or these residues. Question? What does capital F of S stand for? I just grabbed it out of midair. I don't know what it stands for. It could be a voltage. It could be a current. It could be somebody's temperature response. It could be position as a function of time when you inverse Laplace transform. So I just created this capital F of S. It's the Laplace transform of some time domain expression, little f of t. But in this class, it's typically going to come about as a voltage or a current. And we now need to find what is that voltage or current in the time domain. Yes, so now what we are trying to do right here, little f of t is now the script L inverse of the big thing, f of t. And that's what we did in the last two steps. We went from capital F of S in the row one up from the bottom. We inverse Laplace transformed each term individually because it's a linear operation, and we can now isolate on those three terms. And what does this now look like as a waveform? How long will you have to wait before you no longer see little f of t? Which of those exponential decays are the slowest? The e to the minus 2 is decaying slower than the e to the minus 4t. The 5 delta, that happens in an instant. If we're just looking at f of t, now we can concentrate on this 11 e to the minus 2t. And what did we say last time? Oh, if that actually becomes e to the minus 5, then effectively that term is gone. And so we're looking at 5 time constants. We're setting 2t equal to 5. And now what do we end up with? We get a settling time of 2.5 seconds. So in 3 seconds, you can basically, did anything happen? It'll all be gone for this particular f of t. So if that was a voltage and somebody said, what's my transient, or how long is my transient? You can say, well, in about 3 seconds, your transient will be gone. You won't see anything that happened in that system. Did you? Okay, question? How did I get that? Actually, I'm going to get that in a little bit later in another example. Is that okay? Remind me. How did I get the time constants or the 5 tau, one time constant? What's one time constant? I'll try to get that in the next example, okay? I want to try to get further than what I've just now gotten. Okay, any more questions? Let's now continue then with this more general discussion of Laplace transforms. And we're going to go back to the beginning. Now that we've seen some of this, let's now rewind and try to learn it a little bit better. That's my idea here. So what is the variable s? In very basic terms, it's a complex number. It's a complex variable because it is s. So I'm going to say it is a complex, not complicated, but complex meaning it has a real and imaginary component. It is a complex frequency variable that actually generalizes what you finished up with in 220, which was the phasor concept. And contrary to maybe what you're thinking right now, it is designed to help us. The Laplace transform is supposed to be helping us. And one way to think about this complex frequency variable is in the S-plane, which has a real axis. That's the horizontal axis, and typically we will label that or call the real variable a sigma, and the imaginary axis, and sometimes I might say, oh, this is imaginary of s, or this might be the real part of s. This, a lot of times, we associate with omega. And this complex frequency variable, then we will separate into its real and imaginary parts, sigma and omega, and s has units of radians per second. Per second, that's the frequency. Radians, that's now giving us this basically rotation type angular rate or a frequency concept. Let's now look at a particular, suppose we go up here to omega equal to 3 and sigma of -2. Now we would have a point right there. This would be then s equal to -2 plus j3, if my arrow pointed to that spot. And let's now see what that s gets us. Yes?
Is there a minus sign in front of the sigma on your general definition of s?
So in my, I don't know, I get sloppy. The question was, is there always a minus sign in front of sigma? Typically, we do keep sigma to be positive because a lot of the times, most of the time, you want to be having your poles in the left half plane. You want to have some decay. You don't want to be playing with systems that go unbounded with time, which is what would happen if you had something over here that was a part of your system. Now that's going unbounded with time. And so it's just sort of traditional that we say E or S is equal to minus sigma so that sigma becomes a positive number when it's nice. But you may see this many different ways. Somebody might say S is equal to sigma plus j omega. Then you know, oh, my sigma needs to be negative. I hope that doesn't confuse you, so I wouldn't get too hung up on the structure of how I've defined S. Did that answer your question? Let's see what we can do with this concept of this complex frequency variable. So let's look what we can build. You guys are engineers, you like to build things, right? So let's look what we can build. Maybe I'll put that in quotes. No, I won't. We can build. Look what we can build with, I will put this in quotes so that you know that I'm trying to make that S. Let's look at e to the st. Because we know in the very first time we started looking at Laplace transforms, we had this resulting, or we might want to know what's the Laplace transform of e to the st. In the time, if we now replace S with this complex frequency number that we've parameterized as minus sigma plus j omega times t, now is why you learned your, let's say, math material in high school or somewhere. How can we treat exponents? Since they're adding, we can actually pull that apart and have two pieces that are multiplying together. And let's now say that we have an e to the minus sigma t piece and an e to the j omega t piece. The first piece is really going to give us a decay, and the second piece, think of that as a rotating phasor. The picture that you might envision for that rotating phasor, let's say that we're just dealing with a unit length. So now we just have an e to the j omega t. Now you could have this guy spinning around at a rate omega. So this is just rotating around, and if you looked at the real component, if you projected that dot onto the real axis, that would give you a cosine waveform, and if you projected it onto the vertical, it would give you a sine. Let's not get hung up on that. Let's move on. Suppose now that I tell you, oh, suppose v of t is now v sub m e to the st in general, and now you can think, oh, that's a voltage, where v sub m is maybe the maximum value, and it's now scaled by this complex exponential e to the st. What if s is equal to 0? What becomes of little v of t? If we replace s with 0, what does that give us? E to the 0 is always 1. This just gives us v sub m. And that says then that this v of t, how does it behave as a function of time? What's little v of t doing as a function of time? How is it changing? It's not changing, is it? It's constant. Or you could think of that as like a DC, but what was the frequency that we were putting into that formula for little v of t to obtain a constant waveform? Our signal, little v of t, with s equal to 0, corresponds to DC, or constant signals. Does that make sense? What's our frequency? What's S? 0. That's DC. So we have a DC frequency that gives us a constant signal. Suppose we look at a different frequency. Suppose that we now say if, let's say S is equal to j omega. Now we don't have a real part, and are you seeing where these might be in the complex S-plane? In that first example, we were right there. That was S equal to 0. Now what I'm saying is suppose that S is somewhere here on the imaginary axis. It's j omega. That's where we're living with our definition of S as I've defined it here. S is equal to j omega, and you could pick a particular omega. You could say 8. What's going to happen when omega is 8? Now what do we have for little v of t? V of t becomes v sub m e to the s, which is now specified to be j omega times t. And this is actually now a complex spinning phasor. And now it's nice to remember Euler. Euler said e to the jx can be rewritten which way? If you did a Taylor series of e to the jx, you could make that look like a cosine plus a j sine. So this is now cosine of x plus j sine of x. That's Euler. Meaning if we wanted to maybe put v of t back into the real world, or to make it real, we could simply take the real component of the right-hand side for v of t. We could say, just give us the real piece of that complex spinning phasor. You could now go back up here and say, oh, I have a phasor that's spinning around at omega. I'm now just looking at the projection of that phasor on the real axis. And that will now give me the following. Therefore, if we want a real signal, one way to find that or to obtain that is to just take the real part of v sub m e to the j omega t. Now, typically we don't have just one complex value. We have its twin or cousin down below. They come in conjugate pairs, which means we would have one phasor going counterclockwise at omega and the other one going clockwise at omega, and they would be in sync. So really we could be adding e to the j omega t and e to the minus j omega t, and that also gives us a cosine. But here I'm just starting with one pole. This now becomes the real part of v sub m, now imposing Euler, and now we end up with the real part of that complex number, complex quantity, is now v sub m cosine omega t. This is now a sinusoid, or a sinusoidal signal, with, let me say, S equal to j omega. Now let's go the next step. We've looked at just what's happening on the imaginary axis at DC and at any point on the imaginary axis. Let's step off of the imaginary axis and look at values of S. Suppose that we now say if S is equal to minus sigma plus J omega, now what? Now we just replace S again in our expression, which is V sub m e to the S minus sigma plus J omega times T, and we want the real part of that. Knowing what we know about exponents, we can separate that into two pieces that are multiplying each other. The V sub m e to the minus sigma t, that's already real. Let's go ahead and just pull that out front. And then we have the real piece of e to the j omega t. And Euler tells us what's in that second half of that right-hand side. That's just the cosine, isn't it? Because it's cosine omega t plus j sine omega t, and we're just keeping the real piece of that. We now end up with v sub m e to the minus sigma t cosine omega t. This little v of t, when we started with a value of s of minus sigma plus j omega, we now end up with an exponentially damped sinusoid when we started with s equal to minus sigma plus j omega. Let's now look at what that allows us to do when we try to apply these concepts to a circuit. Circuit analysis in the S domain. Suppose that we now have a circuit that has a voltage source. Let's call that V of t. We have a resistor, and we have a capacitor. And we are interested in the voltage across that capacitor responding to this input voltage source V of t. What is that circuit? If somebody gave that to you on a job interview and they said, tell me about this circuit, that's an RC circuit, and it's low pass. So this is a low pass filter, and now we need to see if we can actually justify that through our analysis. So how are we going to write the equation that governs the dynamic behavior of that circuit? What's one way to do that? KCL, we could use KCL, but you guys usually go for KVL, don't you? Mesh. You kind of like to write the mesh equations, so that's what I thought you would want to do. That's what I was going to do. Let's use mesh, but which of these variables do we probably want to focus on? The capacitor voltage. So our strategy is to write these equations in terms of the capacitor's voltage. And that's from ICE. So that now we could say, oh, there's I sub c, and here is v sub r if we needed to label those for any particular reason. And maybe we want to write a KVL equation in that direction. If we do, what's KVL? If we start in the lower left, we have minus v of t plus okay, we want to know what's the voltage drop across that resistor from left to right. And let's just write it in terms of I sub c to get us started. So that now we say, oh, that's now R times I sub c of t. As we've defined our current, that current in the mesh current is equivalent to I sub c plus V sub c of t is equal to 0. And now is when we invoke ICE. That will allow us now to eliminate I sub c of t and just have an equation containing V sub c, its derivatives, and V. V is the input, and V sub c is what we're trying to solve for. Now we have an equation minus V of t plus RC V sub c prime of t plus V sub c of t equaling 0. And you may not see it written in that way. You may see it written to where you have the highest derivative with a coefficient of 1. We might make this monic by dividing everything by RC, and we end up with V sub c prime of t plus 1 over RC V sub c of t, and I'm going to put that, add V to both sides, and I'm still dividing everything by RC. This might be a more standard form for the equation that governs the dynamic behavior of that circuit. What's the order of that equation? 1 or first order, isn't it? How many energy storage elements did we have? We had 1. So, okay, we're feeling better. We're sort of consistent with this. Now let's take that equation into the frequency domain. And we'll do that by Laplace transforming that differential equation. And we can do that term by term. Meaning now we need to Laplace transform V sub c prime of t. The 1 over RC is constant as a function of time, and that's now then 1 over RC times the Laplace transform of V sub c of t. And that's 1 over RC Laplace transform of little v of t. Is it clear where that blue equation came from relative to the boxed equation above? We're just we're Laplace transforming each of those 3 pieces by themselves. Do you remember what the Laplace transform of a derivative provides or produces? That introduces this factor of s that scales the Laplace transform of little v sub c, which is capital V sub c. But in general, when we're taking the Laplace transform of derivatives, what do we also need to keep track of? initial conditions. And this is now minus v sub c of 0 minus. Then we have 1 over RC, and now we are just saying we don't know what little v sub c of t is, but we do know that if we Laplace transform it, that becomes this capital V sub c of s. And we're trying to find an equation for capital V sub c of s so that we can inverse Laplace transform to actually obtain the little v sub c of t. And we can treat the little v of t the same. You give me a little v of t and I can produce that capital V of s. Yes. Why was the first term in this Laplace transformed equation, why did it and only it have an initial condition? Because it was a derivative. Now if we had a second derivative, we would have a couple of terms in there that are initial condition terms. But here we are simply saying, oh, I don't know what the capital V sub c of s or little v sub c of t is, but it's not differentiated. I know that if I Laplace transform it, I just get the capital V sub c of s, and I now am going to try to find a formula that involves capital V sub c of s. And I can now split that into different pieces. Let's combine the terms. That are associated with capital V sub c of s. Or I now have s v sub c of s plus 1 over RC v sub c of s. And that's equal to 1 over RC times v of s plus, now I'm adding that initial condition to both sides, and it's no longer on the left-hand side. Or if I factor out that v sub c of s from the left-hand side of the equation, I now have s plus 1 over RC times v sub c of s equaling 1 over RC v of s plus v sub c of 0 minus. And we actually will refer to this, or it's nice to have a particular way of describing or referring to that, and we're going to call that our characteristic polynomial. And that's what governs the natural behavior, the natural characteristic of this system. If you kicked this system, it would shake based on the characteristic polynomial. What kind of modes does it have just naturally? The response is going to contain not only the modes due to the system itself that it naturally contains, but it's also going to be influenced by the input voltage waveform that we're applying, and that will come in as the capital V of s. We'll just Laplace transform that little v of t. Let's now solve this for capital V sub c of s by dividing everything through by that characteristic polynomial, and now we have 1 over RC over s plus 1 over RC, that's times v of capital V of s, plus v sub c of 0 minus over s plus 1 over RC, where the first piece is due to our forcing function, or the input. That's called our forced term in the response, or will be, and this is now the piece of our response that's due to the initial condition. Our forcing function was little v of t, and the frequency domain, that's this capital V of s. Let's look at some particular waveforms or sources in that. Remember what we're dealing with. It's a low-pass filter. Now we've analyzed that low-pass filter, and this is now the resulting frequency domain governing equation or relationship. Suppose now that somebody says, oh, you know what? The initial condition on that capacitor was 2 volts. And suppose that they also say that we're also going to apply as our input voltage waveform u of t, or the unit step. And we want to now know what does the capacitor voltage look like. If we know that that capacitor was initially charged at 2 volts, and we apply a unit step as our voltage signal that turns on at t equals 0. What's the Laplace transform then of our source? That's capital V of s. That's the Laplace transform of the unit step, and we've derived that, haven't we? And it's in a table now. What's the Laplace transform of u of t? That's 1 over s. We can now plug that 1 over s and eliminate that capital V of s. So that now we have our expression for V sub c of s is now 1 over RC over s plus 1 over RC times s plus, and now the initial condition we said was 2, s plus 1 over RC. Now what do we do? Now view this capital V sub c like our capital F of s at the beginning of today's lecture. What did we try to do with capital F of s? You hit the shift key, right? We just capitalized and uncapitalized these variables. We're trying to take the inverse Laplace transform of this waveform. That means we're trying to find little v sub c of t. And how do we find that from this expression? What strategy did we use to take this into the time domain? Was there any kind of partial something? We did a partial fraction expansion, didn't we? Do we have more than just a single factor sitting underneath or in the denominators of some of these terms? We do, don't we? The 1 looks almost too easy because we have an s times an s plus 1 over RC. But that's a quadratic. There's 2 terms and they're linear. So now we have 2 linear terms. Let's do a partial fraction expansion. The last term we can immediately take into the time domain. I hope you can see that. But the first term on the right-hand side we have to handle with a partial fraction expansion. What does that look like? If this is now capital V sub c of s, what's the partial fraction expansion look like? How many terms are you going to see on the right-hand side? 2, or if we keep the rightmost term by itself, we'll have a third term, won't we? So let's now break that first term on the right into 2 pieces and keep the other one by itself. Or I now have a over s plus a b over s plus 1 over rc, and I'm just keeping this one because that one's easy and it's already done. If I said in terms of A, B, and 2, what is going to be my structure of the time domain waveform for that capacitor voltage? What's little v sub c of t? What happens when I inverse Laplace transform A over S? What does that look like in the time domain? That's just a step, isn't it? Scaled by A. So this now becomes A u of t. What's the middle term become in the time domain? Is that clear where that's coming from? And then if that's the case for the middle term, what's the last term going to yield? That will be 2e to the minus 1 over rc times t, and that's t greater than or equal to 0. If you go through and find capital A and B, you'll actually find that A is 1 and B is minus 1. And now we can say that v sub c of t is 1 minus e to the minus 1 over rct plus 2 e to the minus 1 over rct, t greater than or equal to 0. But those last two terms are exactly the same, just scaled differently. We can combine those, which says that we now have 1 plus e to the minus 1 over rc t. And I could say, oh, switch that on at 0. Or you could write that as 1 plus e to the minus 1 over rct and say that's only valid for non-negative values of time. Yes?
When you did the partial fraction expansion, what happened to the first term numerator of 1 over RC?
So what happened to the, in our partial fraction expansion, we partial fraction expanded this piece right here. And the question was, what happened to this term, 1 over RC? That's just some constant, isn't it? And in our partial fraction expansion, we simply say we will find out what A and B are. They will be some combination or function of that 1 over RC. But A and B will result in, or they will absorb whatever numbers they need to in order to make their combination eventually be 1 over RC if you recombine them back together. So we really don't worry about that. We would need to in terms of keep track of it as a number, but in our partial fraction expansion, it's just A over S plus B over S plus 1 over RC. The 1 over RC gives us the values for A and B. Question? So are we able to say that a unit step is 1? So I'm stating now that these bottom three blue formulas are equivalent. And now I say 1 for t greater than or equal to 0. Isn't that identical to a unit step? So if I replaced, or that black formula, that u of t is actually a little bit redundant in that formula. I have a u of t, but u of t is 1 only for positive values of time. And I'm already saying that with my comma t greater than or equal to 0. And that's where don't think too much about it. It just is a switch, U of t. Now, what does this capacitor voltage look like as a function of time? Do you see that from this formula? If an interviewer now said, well, tell me what that looks like as a function of time. You say, well, it's right there in front of you. Maybe you wouldn't answer it that way. Maybe you would say something like, oh, you want me to proceed? Would you like a sketch? Because you already have it mentally right there in the noggin, right? You know what that looks like. Where are we starting? This is now, we're trying to sketch V sub c of t. Was that a sure? Versus time. Where did we say we were beginning? At 2. We said our initial capacitor voltage was 2. That equation for V sub c of t better be consistent with what we were given. Is it? If we evaluate that at t equals 0, we get 1 plus 1. Last time I checked, that was 2, wasn't it? We're not in that digital logic class where we always have to go 1 and 0, 1 and 0, 1 and 0. Where am I? 2. Right there. Now, where do we eventually end up? So now you could say, oh, let me just think about this. And you say, I'm starting at 2. Where do I eventually end up? Well, let me look at that formula as t gets really, really big. What happens? The 1 doesn't do anything, does it? It stays. But what's that second term doing for us? That vanishes. So eventually we better end up at 1. So we're moving from 2 to 1. And how do we move? As an exponential. So now, if you were sketching this for your interviewer, you could then say, okay, then this is what it looks like. And now they're going to say, well, where does it sort of get to that 1? I'm now answering the earlier question. When does this now effectively become 1? When does it become 1? When you could say, when e to the minus 1 over RCT becomes insignificant. Right? That's when it becomes 1. But what is insignificant? That's sort of an engineering decision. But typically we say, oh, if we're within 1% of where we started, that's insignificant. In that case, have you ever played with your calculator and just said, how big is that? You haven't? You guys never cease to amaze me. E to the minus, no, I'm teasing. But what is e to the minus 5? Do you have a calculator there? E to the minus 5 is 0.0067. You don't need any more than that. So this is now 0. I'm not putting this into mastering, so I just am going to use 2 significant digits. You may need more than that. Oh. So this, we have agreed, this is smaller than 0.01, which is 1%, right? So this is small. Right? It's small. And that's actually 5 time constants. Remember when they were saying, oh, where do you get to e to the minus 1? Do you remember what that was? 1 over E. That's okay. That's that's a correct answer. 1 over 2 point something, 1 over 2.7 something. E to the minus, don't you kind of remember that? No? 0.37. Plug it in, plug it in. Plug it in. So I was rounding 0.37. So that's 37%. That's this exponential curve. After one time constant, you're at 37% of where you started. After 5, you're down below 1%. Do you see that progression? And now I know you're going to run home and just be going e to the minus 2, e to the minus 3, e to the minus 4. E to the minus 4 is 4 time constants, and that's 2%. And in a controls class, a lot of times you play with, what's my 2% settling time? What happens in 4 time constants? So now, this is representing 1 time constant, which says that if we had something like we had before, we had e to the minus 1 over RC t. Did we not? Now we're saying we would like to know what value of time t will give us e to the minus 1. This is 1 time constant. That's this tau. And this is doable, right? Now we're setting that equal to that. So that now we can look at this and say, oh, we have 1 over RC times tau is equal to 1. Our time constant tau is RC. Have you heard that? What's your RC time constant? You will. If you get into 351C and somebody says, what's your RC time constant? I know. What's my R and what's my C? You multiply those together and you're going to have a time. That's a time constant. So we didn't specify what R and C were in this problem, did we? But if somebody gave, if you went to Josie and you said, I need my settling time, my 1% settling time, Josie, to be 2 milliseconds. Can you give me an R and a C and a first order low pass filter to yield that response? See if she gives you an R and a C. She'll go get it off the board. Tell me what you want, right? But you now know how to do that. Here's 1 time constant. What's 5 time constants? 5 RC. So now that's how far or how long it's going to take you for your system to settle to its final value. And what was the final value of this particular circuit? For the initial condition that we said, which was starting at 2, this is decaying to 1. So now, in terms of our settling time, I may not even put that 1% as an adjective in front of it. I may just say my settling time is now 5 tau. In this case, that's 5 times RC, where this is our time constant. And this is our settling time, and we might call that T sub S. Judging from all the zippers, it sounds like we've reached our settling time. But we haven't. We still have a lot of time left. So let's squeeze it in. Suppose that we said, you know what, that was fun, let's do another one. Suppose that we now have that capacitor is not charged initially. It's 0 volts. And now suppose that somebody says, suppose that I now excite that low-pass filter with a cosine. And I'm turning that cosine on right at t equals 0. What does the source Laplace transform look like now? What's capital V of S? What was it when it was a unit step? 1 over S. Now what is it? Now you're just Laplace transforming A cosine omega t. Please, please get this right on your homework or on the exam or both, right? This is a give me. This is a gift. What would this be? If you don't know it now, you'll know it by Sunday evening, right? This is A, and this is the cosine, so now we have S over S squared plus omega squared. That we would now plug into our formula here, and we don't have that initial condition term anymore because we had 0 initial conditions. We plug in that capital V of S, and we can solve it. We can do another partial fraction expansion, and what's going to happen? What's going to happen in this low-pass filter? What kind of terms are you going to have in your system response? V of S has what in the denominator? A cosine. It's shaking, right? And it just keeps shaking, and it's not decaying. It's a bad image, isn't it? But you'll never forget it. It's a cosine, and what you have a little transient due to that RC time constant. We'll pick up there on next time we meet.